to improve community resilience to natural hazards. Scientific workflow applications automate the flow of information from one component to the next, and this facilitates the automation of larger and more complex tasks. We build software tools using this framework and release them for use by the natural hazards engineering community with the aim of fostering collaboration across scientists, engineers, and others who seek to improve community resilience to natural hazards. Our software development activity is guided by the Grand Challenge reports, which identify what type of software is needed by the natural hazards engineering research community. And there is convergence with regard to these three aspects, that software should support uncertainty quantification, tools should support performance-based engineering, and we should support community resilience by looking at large regions and modeling recovery. The SimCener scientific workflow shown on the slide can handle all of these requirements that we have identified, and we build our applications in the spirit of the statement there. So with regards to the uncertainty quantification, for example, the quote from the Grand Challenge report shows that dealing with uncertainty is unavoidable in natural hazards engineering, and analysis without accounting for uncertainty can give false insights or false confidence in the results. So today we will outline how SimCener tools will help you incorporate uncertainty in your analyses. Right. So regarding the second point that was on the previous slide, so we see that the performance-based engineering framework explicitly considers uncertainties during all the stages of analysis as shown in this graphic. These uncertainties arise from several sources, including inherent randomness in the hazard or in material properties, for example. And there is also significant uncertainty regarding the choice of the models used in the analysis and the value of the parameters used in these models. So the result of all of these uncertainties is that decisions need to be made under uncertainty, and this results in inherent risk. So the SimCener's workflow supports development of applications for performance-based engineering and for modeling community resilience. SimCener applications are not running deterministic analyses, but are running UQ workflows, which gives some measure of uncertainty in the response quantities. So this means running a lot of simulations and not just one. And this slide, this shows how the SimCener scientific workflow system allows the creation of research applications which automate more complex tasks. So this is done by chaining components together in an application, and the user does not need to intervene to pass data output from one application to the next. The applications released by the SimCener are all free and open source, and they consist of a front-end user interface and a backend which drives the analysis. So the components shown in that slide are the components that are part of the backend. And these components in the backend are interfacing with applications either that are built in the SimCener or that are with existing external software. For example, the quoFEM application consists of the UQ and the FEM component of the backend, along with the cloud computing component, which makes running large numbers of complex simulations feasible. Other applications for response estimation, like the EUQ application, build on the features in quoFEM. The PBE builds on response estimation tools and enables performance assessment. And R2D uses all the components to enable regional scale simulations. So today we will give an overview of the methods available through the UQ component and in the quoFEM tool. Sangri will now begin the introduction to the UQ methods.
Thank you, Akash. So we will now go through briefly what kind of UQ analysis method are there for you to perform. And it has two categories. First is forward UQ analysis. So why is this forward? We want to propagate the uncertainty from inputs to outputs. Suppose you have a simulation model, say a building model. This building has several parameters which its values are not precisely known always. And even the excitation is uncertain. And because of the randomness coming from these values, our response of interest, say maximum displacement of a structure, is also uncertain. That means it has mean, but also it has some variance. And then you can think of a threshold level that defines the system failure event. So if system response is bigger than certain threshold, then this system can be failed. So now, based on this distribution at threshold, we can identify what is the probability that this system will fail. And now interesting question arises here. Consider there is an alternative design, say you have different material properties, and now we have different response distribution. Then among two design choices, which one would you select to be better? The thing is, if you run only deterministic analysis, it's like similar to comparing only the mean values. That means the original, you are likely to select the original design to be better because it has smaller mean response values. However, if you also consider the variance, the fact that alternative design have much narrower variance scale, then you will see that probability of response being bigger than threshold is actually very small. So I would say alternative design is a better design. So this kind of insight can be gained only by incorporating uncertainty in your analysis. So what is forward UQ? Based on assumptions on inputs, you want to predict the uncertainty in outputs. The example can be mean expected recovery time after a disaster happens, or standard deviation of repair cost, maybe probability of significant damage occurrence, or even you want to compare the importance of each random variables. So these three are big categories of forward UQ analysis. So I want to go through these three one by one with this simple one random variable and one response example. But before we start, I want to address this question which we often get. So people are saying we have a simulation model. We know what our parameters are, but we don't know how to assign the probability distribution of this. So I want to briefly talk about this. So probability distribution of parameter tells you how probable each value is to be certain parameter. So for example, if you consider Young's modulus, mathematically speaking, it can be any values. It can even be negative value because that just means that if you push a building, the building will come forward instead of going backward. But your engineering judgments tells that that's no way true because you never observed those. So engineering judgments plays an important role in deciding the PDF, probability distribution function. So based on your insight on the physics of the quantity, what you usually do is select a simple distribution and apply reasonable limitations. For example, if you know the range of probable range of interest, then you can set uniform distribution. But if you have better assumption on the value, for example, Young's modulus of steel will be around 200 gigapascal, then you might want to introduce Gaussian distribution. But if you want to further reduce the subjectivity and be more precise, then there are studies performed previously to investigate what distribution you should use in certain situations. So there are literatures which tells you which distribution and parameter you need to use. And further, if you actually have the data that indicates which about this, for example, this Young's modulus values, then you might want to combine your engineering judgment with your data set. And this methodology is called Bayesian updating. And Akash will come back later to give you what the idea on the Bayesian updating. But now let's first consider forward UQ analysis. The first category is forward propagation. So the aim of this approach is to identify mean, standard deviation, or probability distribution of the response. One straightforward approach is so-called Monte Carlo sampling. That means you generate a lot of samples of Young's modulus, which will be, you will have lots of samples around, say, 200 gigapascal and several samples for the extreme values, like maybe 220 gigapascal or 180 gigapascal. And then say this is the histogram of samples. and you want to give this sample to your simulation model and run lots of simulations using the cases. And then it means you will get lots of response samples as well. And if you draw a histogram of these samples, then that kind of approximates the response distribution. So this is how fundamentally Monte Carlo sampling works. However, when your model is numerically expensive, then you don't want to run this much simulations. So to reduce the number of model runs, there are other algorithms available, such as like thin hypercube sampling, surrogate modeling, or even multi-fidelity modeling. And there's second kind of for DQ analysis, which is called reliability analysis. So in this case, we additionally have a threshold level of interest. So we want to identify the probability of our response exceeding a threshold level, because that indicates the system failure. Of course, a straightforward approach will be Monte Carlo sampling. So you generate a lot of samples and count the number of samples that exceeds the response threshold, and then divide them by the total number of samples. And that is the probability of this failure event we defined. However, when your model is very expensive, and also when the failure probability of interest is low, then you will want to reduce the number of simulations by introducing so-called advanced reliability methods. So why does the failure probability matter here? I'll give you an example. Say if your probability of interest is 10%, then to estimate this 10% precisely, you need to have at least 1,000 simulations. However, if your probability gets smaller than say 0.001%, then it will require you at least 10 million simulations. And you don't want to run this with your expensive simulation model. And unfortunately, in natural hazard engineering or civil engineering, the latter is the case, because we don't want our building to fail so easily. In such cases, again, we have some advanced UQ algorithms, such as importance sampling or surrogate modeling, or we can even combine both approaches. And by doing so, the number of simulations can be reduced to several hundred, and in certain cases, it's even less than 100. So that's gaining a lot of efficiency, literally making impossible to a possible situation. And finally, the third method has slightly different context. So now we have multiple random variables of interest, and there is single response we have. And at one point you start to wonder, are all the random parameters equally impacting the response? And you know the answer that it's not. Then you want to identify what are the variables that are really influencing the response compared to other random variables. So this is the kind of question global sensitivity analysis can answer. So here we have two variables instead of one. And just to illustrate what is happening in sensitivity analysis, consider Monte Carlo simulation. Say you generate a lot of samples of two random variables, you pass each of them to computer simulation and then run analysis to get the samples of response. Now, given this sample set, you can draw something like first random variable versus the response. So it will be some kind of scatter plot. And you can do the same for this second random variable. And by comparing these two plots, you do have kind of idea on which random variable is more influential. Say if you see the second plot, it's really hard to tell whether each strength of column is actually impacting the maximum displacement or not, because it does not show any trend. So you have intuition that the maximum displacement is more sensitive to change in the first random variable compared to the second random variable. And what global sensitivity analysis does is to change this intuition into the quantified number that ranges from 0 to 1 by comparing how rapidly the trend is varying and how much is their variance are. And based on this, you can make conclusion like, okay, maybe its strength of column is not as important as other variables. And then I might even consider treating this as deterministic variable as opposed to random variable because it's not really affecting the response. I have slide for surrogate, but because of the time limit, I will just move towards this presentation to Akash for the inverse uncertainty quantification.
Thanks, Andrew. So the aim of inverse UQ analysis is to update the assumptions that can be used in forward analysis, such as the probability distribution of the inputs to be used. Or if we are given a set of plausible models, we might be interested in selecting the best model from among the set of models that we have considered. So that these are two kinds of inverse problems. And we do this by updating based on data collected about observable quantities. And then we make inferences about unobserved quantities. For example, we might use values of the measured roof acceleration and then use predictions of the same output quantity as that was observed from the model, and then use that information to update the distribution of the inputs to that model based on that data. So one type of inverse problem is model calibration. So in the Bayesian approach to model calibration, we update the distribution of the inputs to be consistent with the observations or with the observed data. So we have seen that in forward analysis, we can obtain the distribution of the outputs given inputs, but during model calibration, we use the observed values of the outputs that correspond to the dots on the y-axis in the rightmost plot there. And then we update our belief about the input distributions to be used by using Bayes rule to do the updating. So the data could come from instrumented structures, or it could come from experiments with physical models, or it could be the output of high fidelity simulations, simulation models, etc. So given some distribution of the inputs, Bayes rule is then used along with the data to update our belief about the probability distribution of the inputs. So after Bayesian calibration, the output, the updated distribution is characterized in the form of samples drawn from the so-called posterior probability distribution. And these sample inputs can then be used for doing forward propagation through the various types of forward propagation forward problems that Santanu discussed. So some examples are, we could get data from experiments for regarding the material response of a material model that can be used for calibrating a material model, or we might have data from a high fidelity model, and we can use that data to calibrate a reduced order model. Or yeah, we might use, we might have an instrumented structure, and then there might be an event, and we can get post-event data from that structure that can be used to do damage diagnosis and prognosis. Or also we can do this in real time by developing digital twin of a structure. So that would be recursive Bayesian updating. And we can also update reliabilities based on the samples drawn after Bayesian calibration. Another kind of inverse UQ method is model class selection. Engineers, we always work with models, and that the models may be physical or mathematical, but every model is an approximate representation of reality. And there is that very famous aphorism by George G.P. Box, attributed to George G.P. Box, that says all models are wrong, but some are useful. When there are multiple models which are plausible and we don't know which model to prefer over the others, then we need a robust quantitative tool to pick the best model out of the considered set of plausible models. So this can again be performed using the Bayesian machinery, where we first calibrate all the models in the set at the first level. And then at the second level, we update the probabilities that are assigned to each model in the set. And the models that we would have considered might be either complex or they might be simple, and we might be concerned about overfitting to data for complex models. So this is where the principle of model parsimony helps. It balances the goodness of it against model complexity, and this is automatically done during Bayesian model class selection. And once the model probabilities are assigned, we can either proceed by model selection or model averaging. So in model class selection, we just pick the best model from the set and use that one model for making predictions. Whereas in model class averaging, we select all the models or the best few models and then take weighted average of the predictions from these models. Yeah, so that brings me to an end of the overview of the inverse problems, and Sangri will briefly give an overview of quoFEM.
Thank you, Akash. So there are some software packages and toolboxes to help you run UQ analysis for your deterministic models, and quoFEM is one of them. So what is different in quoFEM to other tools is that we have graphical interface, and we took lots of care for the interface to make you incorporate your FEM application easily with our UQ method. So we like to say that you bring the FEM model and we will take care of the rest. But note that this does not mean that we don't want you to know anything, because we are basically open source software. So when you get used to UQ analysis, there will be some point you want to get more degree of freedom on your UQ algorithm. So in that case, you can go to source code, making modification on that, and then build your own quoFEM. And this is much easier than building the new algorithm by yourself from scratch. So quoFEM can really accommodate from very beginners to advanced users. And this shows you kind of current status of quoFEM. So given your FEM model from different sources of engines, this custom can include, of course, something like ETABS or Abacus. You can run different UQ analysis, including forward, inverse, and even surrogate modeling capacity. And you can switch between them by clicking buttons. So this briefly shows how quoFEM user interface is. So here you can select UQ method in this tab and which algorithm to use, and then give information on FEM model you have, and tell us which variables are which parameters will be treated as random variables and what are parameter values you want to use. And then tell us what are the response quantities of interest. And after filling in this information, if you click run button, it will give you the results. And all the intermediate files are also saved in your local computer. And this is example of sensitivity analysis result. It shows you that we don't know what this model is now, but we can say that, okay, this parameter AU is not affecting the response according to this sensitivity analysis. So maybe we don't have to consider this as random variables. So you can make decisions, something like that. And so as a conclusion, an estimate without a standard error is practically meaningless. This is because deterministic results are just one of many possible outcomes, but this is not enough. In order to make robust decisions, we need to also know how probable each outcome is. So there are many tools available to help your UQ method, and they are really nice ones, and quoFEM is also definitely one of them. So I think this concludes our presentation today. Thank you very much for attention, and I hope this was helpful for you.
Thank you so much, Sangri and Akash. And would it be possible to have a copy of the slides so that we could share them with the membership?
Yeah, of course, we will be happy to. Yeah.
Wonderful.